Okay, good morning guys. Here's our next video lesson on probability. We are going to use the same ideas we learned last time and kind of just add a little wrinkle to it. So this is what we looked at last time. You guys did great in the homework, so I'm not too worried about this. But here's my little spinner. The theoretical probability of spinning a 4, I can spin it, but that's different. Ooh, I almost got it. The theoretical probability is what we would expect to happen. So that's what we're going to work on today. So there's 10 squares. The 4 is one of those, squares, not really a square, but one of those slices on the pie. So 1 out of 10 chance of getting a 4. My odd numbers, I have 1, 3, 5, 7, 9. So I have 5 odd numbers out of 10 total spaces. So my theoretical probability is 5 over 10 or 1/2. So that's different from the experimental or the empirical, I think I called it, where it's what should happen if we were to, get a perfect trial. So a lot of you guys did a really good job on that. The more we spin, so if I spin this wheel 500 times, I should have about 1 out of every 10 spins be a 4. All right, but if I only spin the wheel one time, I could get lucky and hit the 4 just that one time. So that's what a lot of you explained to me on that roulette wheel question. In the short term, you can get really lucky and hit all your numbers right away. But over time, the theoretical probability is going to win out, and that's why the casino, always wins money because the odds are in their favor. So that you can win money in the short term, but the theoretical probability in the long term always wins out. So let's look at another question. If we spin the wheel twice, what is the probability of getting a 5 the first time and then a 7 the second time in that order? So the probability of getting a 5 we know is 1 out of 10, but I'm going to show it to you in a little different way. So let's say, we think about this like a tree. This is a really nice way that always helped me do these probability questions. 3, 4, 5, 6, 7, 8, 9, 10. So that's not perfect, but these branches represent all the numbers I can spin. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So if we want to get a 5 and then a 7 to win it, that's the only way we can win. I have to follow this 5 branch, if you know what I mean. That's the only way that I'm saying we're going to win. If we're going to get a 5 followed by a 7. So now that I followed my 5 branch, now I'm going to do it again. 5, 6, 7, 8, 9, 10. You got the idea. Okay, so if you guys follow my logic there, this represents my first spin. So I got my 5. I got the 1 out of, there's 10 chances here. I got the 5 that I needed. Now after getting that 5, I'm going to follow the branch, and now I'm going to have to spin that 7. So we can think about it the same way, 7, 8, 9, 10. I have an extra branch there. That's okay. So after I follow that 5, now I have to follow the 7 branch. All right, but remember, this 10 possibilities could happen after getting the 1. They could happen again after getting a 2. They could happen again after getting a 3. They could happen again after getting a 4. Every one of these has its own 10 branches off it. So to get the 5 followed by the 7, I have to follow the exact right path to get there. So I can't go from the 1 and then to the 7. I can't go from the 8 and then to that 7. I have to follow the exact right path. I have to follow my 5 branch, and then from that 5 I have to go off onto the 7 branch. So if you count all the possibilities here, I had 10 possible spins, 10 possible numbers the first spin, and then off each of those spins I had 10 more numbers. So 10, 10 more, 10 more, 10 more. So what I actually had was 100 different possibilities here, and only one of them is the winner. So to get a 5 and then a 7 in that order, look how crazy that number gets so big so fast. So this is called, that's called an independent probability event. So we're going to talk about that real quick in this video. It's very much like what we did last time. All right, so I always think about this in terms of like games at the fair or games at the casino. So let's say we have to flip a coin and then spin a wheel in a specific combination in order to win. So we have to flip heads on the coin, which I didn't get. So now my turn's over. I lost no matter what. I have to flip heads on the coin. There we go. And once I flip heads on the coin, I then have to spin red on the wheel. Let's see if I can do it. No. So we can see it takes these two things in order to happen. So I made another one of these tree charts here. All right, so you can jot some notes down if you want. But here's my heads, here's my tails. That's the first branch. So in order to get to the next step, I have to go this way. I have to follow that branch. So all these are losing possibilities down here. And after getting that heads, I have to then hit the red section of the wheel. So if we look at all the possible outcomes, I have 1, 2, 3, 4, 5, 6, 7, 8, 9, 10 possible outcomes, and only one of these branches is the winner. So my probability here is 1 out of 10. So it's really easy actually to do this. All you have to do is multiply the two probabilities together, and that's what my note is going to say here. So two events are independent if the chance of one happening does not depend on the other one happening. So like if we flip a coin twice, the first flip does not change what happens on the second flip. Same thing in this little example here. Getting heads or tails does not affect how my wheel spins. So all we're going to do, the probability of both of these things to occur is the product, so the multiplication of the two probabilities. So the probability of A happening times the probability of B happening. Okay, so if you need to pause and write this stuff down, I don't want to make the video too long, so I'm going quickly, but if you need to pause and jot any notes down, this is kind of the main idea right here. That's the main idea of what we're looking at today. So let's say tomorrow there's a 30% chance of rain. So that basically means 30%, or we know we can think about this as 3 out of 10 probability. 30% is 3 out of 10. We know there's a 30% chance of rain. So if I wanted to do my tree chart, I could make 10 branches, and I don't know if I'm doing this right, and 3 of them would be winners. 1, 2, 3 of those branches out of 10 would be like the rain branches. I'm not going to bother with that. I'm just going to show it as a probability here. This will make it a little easier. So I head out to do some errands in my car. I know we have an umbrella in one of our 2 cars, either my car or my wife's car, but I forgot to check if it was in there or not. So basically I have a 50-50 chance, right? So I have a 50% chance of having an umbrella. It's either in the car I have or the car I don't have. So what's the probability that I go out and I get stuck in the rain with no umbrella? So I have these 3 branches out of 10 for this one. But for this I have 50%, I have 1/2. I have 1 out of 2 branches to win. So again, I could make 10 branches here, 3 of them would be rain, and then off of those branches I either have the umbrella or I don't have the umbrella. I have the umbrella or I don't have the umbrella. Long story short, easy way to do this is I take my 3 out of 10 and I multiply it by my umbrella probability. So there's my rain probability here, and here's my umbrella probability here. Okay, so in order to test my probability, I multiply these 2 fractions together. So if you have a calculator or just do it on your phone, that's fine. These fractions are very straightforward. We just multiply the numerators. So 3 times 1 is 3. 10 times 2 is 20. So I have a 3 out of 20 chance of getting stuck in the rain without an umbrella. Okay? So that's what we do. We take the probabilities, we multiply them together. So now one more thing. Let's say the events are not independent. So like this is an example, like you take a card out of a deck of cards, you don't replace it, and then you draw another card. So 2 events are dependent. If the second one happening depends on the first one happening already. So it's the same rule. We just multiply the 2 probabilities together, but the second the second event is a given that the first one's already happened. So that was kind of a confusing explanation, but here's what I mean. So 2 cards are drawn from a deck without replacing them. So what is the probability of both of the cards being read? So for those of you who don't know, there's 52 cards in a deck. Half of them are red, half are black. So 2 cards are drawn from a deck without replacing them. What is the probability that both cards will be read? So my first pick, I have 26 reds out of 52 cards in my deck. 26 out of 52. I could also reduce that down to 1/2, right? Now, once I take that red card out, this is saying I'm not putting it back in. So now instead of having 26 cards to pick from, I only have 25 cards to pick from, 25 reds left. And instead of having 52 cards in the deck, I only have 51 cards in the deck. All right, so you can see the difference. It's one less to pick from. So if I were to multiply these together, I did this already, I would get 25 out of 102. That would be my probability of getting 2 red cards. All right, so it's just up to you to think really carefully about what you know. Okay, so I'll let you try this one out on your own. See if you can come up with the fractions. I'm going to pause my video so you can try it out, and then I'll unpause it, and I'll show you my work. All right, so go ahead and try these couple out right now. Pause my video and do some scratch work. All right, so here's my work. So the first thing to think about, there's 8 total coins. There we go. In this bag, 4 pennies and 4 quarters. So the probability I choose a quarter, put it back in, and then choose another quarter. So the first, I have a 4 out of 8 chance. I put it back in, so I still have a 4 out of 8 chance. That's the independent situation. That's like the first example we talked about today. All right, so if I multiply those through, I would get an answer of 1 out of 4. All right, so I'm putting the quarter back. That's the key. For letter B, I'm choosing the penny and then a quarter, but I'm not replacing the penny. So this is the dependent. It matters that the first penny was chosen. So for this question, I have a 4 out of 8 chance of picking the penny, and I put the penny off to the side, so it's no longer in the bag. The quarter probability, I still have 4 quarters to pick from, but now I only have 7 coins in the bag. So now when I multiply these out, I get 2 out of 7. So you can see how much the probability changed by not replacing that coin the second time around. Okay? I'm not going to go through all the rest of these. I hope we have the right idea. If you do, you can pause on this screen and try these out. Maybe I'll put the work up here again in a second. I won't explain it all, but I have one more question to show you, and then we'll be done. Okay, so there's my work for this one. If you tried it out, I have 10 total cookies, and then I just need to take into account that I'm not putting it back, and then look at the probability of picking either the chocolate chip or the peanut butter. Okay, so if you have questions, shoot me a message. I want to show you one more quick thing. I think this is a fun thing to think about. I think I wrote this question last year when that Powerball was like $1 billion or something crazy like that. So what are the odds of one of us winning the Powerball? So in order to win the full jackpot, you have to get every one of the white ping pong balls correct, and you have to get like the Powerball, the red ball correct. That's to get the max prize. So there's 69 of these white ping pong balls and 26 of the red. All right, so every time, I don't know if you've ever seen the Powerball get drawn in the news or whatever, they have a big bin of ping pong balls, and one gets sucked up, and then they pick another one, so it does not get replaced. So for us to win, we have a 1 in 69 chance of getting the first ball right. It doesn't get put back. So now there's 68 left. To get the second one right, we have a 1 out of 68 chance. And then we have a 1 out of 67 chance. There's 5 picks of these white balls times 1 over 65. Okay, and then if that's not enough, we have a 1 out of 26 chance to get the red ball right. So this represents the 5 white ping pong balls, and there's my red one. So multiplying all that out, it's a gigantic number, and that's why it's so hard to win. All right, so that was a cool example. There's one like that on your Google form for homework tonight. So let me know if you have questions, guys, and I'll talk to you next time. Bye.